This is the section 1.5 demo for Math 204. Consider the polynomial equation 2x to the fifth minus 10x plus 5 equals 0. So the left-hand side, the polynomial, is continuous, so that's an important thing to note. Imagine that we have no technology available to us to find approximate solutions to this equation. How can we know that solutions exist without actually solving? So I could look at a couple of different x values. I'm going to look at -1 and 1. So if I plug -1 into the polynomial 2x to the fifth, I'll call this f of x, 2x to the fifth minus 10x plus 5, I get 2 times -1 to the fifth minus 10 times -1 plus 5, which is 13. And if I plug 1 in, I get 2 times 1 to the fifth minus 10 times 1 plus 5, which is -3. So I know 2 points on the graph now. I now know that when x is -1, y is 13, and when x is 1, y is -3. And I know that f of x is continuous, meaning I have to be able to connect these 2 points without picking up my pencil. So I have to cross the x-axis somewhere in here at least once. It could look like that, right? Or it could cross more than once. It could look like that, right? And it could cross 1, 2, 3 times, but it has to cross at least once. There's no way to connect those 2 points without crossing the x-axis. So we would have to cross it at least once. So I know there is a 0 somewhere in between -1 and 1. So f of x equals 0 has a solution in the interval -1 to 1. Somewhere between -1 and 1. We cross the x-axis. Once we know a solution exists, how could we know if there's more than one, right? So I know there's at least one in there. At least one in there. How do I know if it's the only one? Well, now I can use a little calculus. I can look at the derivative of 2x to the fifth minus 10x plus 5. So because that can tell me whether my function is increasing or decreasing, where it's increasing and decreasing. Fifth minus 10x plus 5, which is 10x to the fourth minus 10. Figure out where that's 0, and that happens at x equals plus or minus 1. We make a little sign chart, -1, 1. Look at the fence. We're going to look at f prime here. If you put something less than -1 into the derivative, I'm looking at the derivative function right now. Put something less than -1 in, like -10, we get a positive number. Put in something between -1 and 1, like 0, you get negative. Put in something a lot bigger than 1, you get positive. So that tells me that between -1 and 1, f is always decreasing. So I know that I have to be able to connect -1, 13 to 1, -3 with my function always decreasing, right? F has to always be decreasing. It can't ever increase, so that tells me that it can only cross one time. There is a unique solution to the equation I'm trying to solve. Okay, so this is not really a differential equations problem, but it's a way to demonstrate what existence and uniqueness of a solution means. Okay, so this first part where I said, okay, well, if you have a positive value at -1 and a negative value at 1, a solution must exist, right? If I have to be able to connect these without picking up my pencil, I have proven existence of a solution. At least one solution exists. Then I did something with the derivative to show that the solution between -1 and 1 has to be unique. There could only be one. So what's different between what we're going to look at and this theorem that we just did is that the theorem we just did is for an algebraic equation. It was a polynomial equation. We were just looking at solutions that are numbers. Okay, so we are going to look at an existence and a uniqueness theorem for differential equations, which is somewhat analogous but not the same. Okay, so here's the summary of the existence and uniqueness theorem for differential equations. So if you're given that dy dt is some function with t's and y's in it and has some initial condition, then 1, if the function f of ty, the right-hand side of your differential equation, is continuous at the initial condition, we know a solution exists. So that is analogous to what we did up here, right? We had to know that the polynomial was continuous so that we'd have to connect these without picking up our pencil. So part 1 for existence, you need continuity. All right, and then if the partial of f with respect to y is also continuous at the initial condition, we know the solution is unique. So here we just looked at the function. You just look at the function f of ty. If that's continuous, you have existence. Then we look at the derivative. If that's continuous, we have uniqueness. Okay, so let's apply this. We have an initial value problem, dy dt equals 1 plus y squared, y of 0 equals 0. Verify that a solution exists and is unique. So for existence, we have to consider the right-hand side of the differential equation, 1 plus y squared. Because that is continuous everywhere, because 1 plus y squared is continuous for all y, and in particular, the initial condition at the point 0, 10, we have existence. A solution exists. And then for uniqueness, we have to look at the partial with respect to y, the partial derivative with respect to y of 1 plus y squared. So if you haven't taken Calc 3, all this means is that y is the only variable. You would treat any other variable that shows up in here as a constant. Because we only have y in the function anyway, so it's just looks like a normal derivative in this case. So the partial with respect to y of 1 plus y squared is 2y. Oh, sorry. The initial condition is 0, 0, not 0, 10. Okay, so because 2y is continuous everywhere, it's a line. Lines are continuous everywhere. And then in particular, at the initial condition, 0, 0, the solution is unique. Okay, so we have a differential equation, dy dt equals 1 plus y squared with an initial condition, y of 0 equals 0. This theorem tells us that a solution exists and it is unique. So a unique solution exists to this problem. So let's use the slope field to sketch the solution. Supposedly there is a unique solution to this ODE corresponding to y of 0 equals 0. So I'm going to put in the initial condition, 0, 0, and try to follow the slope field, and it looks something like that. That does look like a unique solution. So let's solve it using separation of variables. Find a formula for that thing. So I have 1 over 1 plus y squared dy equals dt. Integrate, integrate. 1 over 1 plus y squared, that's the derivative of arctan. So this is arctan y equals t plus c. And then I'm going to solve for y by taking the tangent of both sides. So we get y equals the tangent of t plus c. And finally, we use the initial condition to solve for c. So y equals the tangent of t, which is 0, plus c. And I forgot to change y to a 0. So I'm making the y 0 and the t 0, and I'm going to solve for c. So 0 equals the tangent of c. So I want to find a point on the unit circle that has a tangent of c, a tangent of 0. Okay, so that happens right here at 1 comma 0, because tangent is y over x, 0 over 1 is 0. So c is 0. So my final solution is y equals the tangent of t. Okay, so there is a unique solution. We found it, it exists, and it's unique, but it is not guaranteed for all t. The theorem guarantees that a solution through the given condition, given initial condition, exists and is unique, but that it doesn't exist for all t, only for some interval around the initial condition. And in this case, that interval is negative pi over 2 to pi over 2. Because that's where the graph of tangent exists.